Okay. You don't wear glasses today. You have a drop in the number of glasses. Well, okay. Good afternoon, first of all. So I will continue talking about probability distributions, random events, and so on and so forth. Do you have any questions regarding what I talked about yesterday? Did you have a chance to look at and compute, for example, check that the sum of the probabilities of the occurrences two dice is 1? Okay. Good. So let's talk a little bit more about the binomial distribution. So let me remind you that this is a very important distribution, okay? And it's a distribution of when we count the number of occurrences of something, okay? So if we have an event ek like we toss n times a fair coin, and we add head or tail, and we ask whether and ek is the event in which we have k tails, for example. Exactly k tails, not at least k tails. Okay. So, you have a question? No. Okay. So the probability is pk is equal to the binomial coefficient, okay, which is indicated like this. Then we have 1/2 to the k, 1/2 to the n minus k. In this particular example of a fair coin. Otherwise, instead of 1/2 and 1/2, we have to put what? Where p is the probability of tails or head? Tails. Okay, so this is to the power k, and the conjugate probability of the conjugate event is 1 minus p, which we call q. Okay, so let me allow for. Okay, so this is the probability of an integer number occurring between 0 and n. And in fact, this probability is well defined when k is between 0 and n. Okay, so this looks more or less something like this. Suppose we have n, which is, I don't know, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, so n is equal to 11. And we can, for every value of k, 0, we can put down a number. Okay? So what's the number that we have to put for k equals 0? Okay, so for k equals 0, we have to put the number n factorial divided by 0 factorial times n factorial. What's 0 factorial? 1. Okay. You know this. So this thing is 1. Okay. So this k is equal to 0, so we have here q to the n. So for example, I don't know, if q is 1/2, we have 1/2 to the 11, which is 2 to the minus 11, which is a small number. It's 1 over 2,000. And then, so we have this small number, and then keeps growing a little bit. It's a maximum, and then comes down. And for n equal 11, we have to put 11 over 11 factorial. So this becomes 11 factorial divided by 11 factorial, and then we have 0 factorial again. It's again 1. Because remember, this number counts the number of configurations that have, if you have all tails or all heads, there is no other configuration that you can get by permuting, right? Any permutation you do, you will end up with the same. So there is only one configuration that corresponds to this, so this is correct. But now we will have, this will be 0, so this will be 1, and this will be p to the 11. That, in case of a fair coin, is again 2 to the minus 11. Okay, so we have a distribution in this sense. It's a discrete distribution because the set of events is discrete. You cannot have 1.5 tails out of 3. Okay, and moreover, this depending on p and q, you can have some symmetry. If p is equal to q, you can have a symmetry with respect to n minus k. Okay, if we reflect, if we exchange k with n minus k, we have a symmetry because in one case we are talking about heads and tails. But if the coin is fair, then the probabilities have to be equal. Like the probability of having 2 heads out of 10 in 10 trials is the same probability of having 2 tails in 10 trials. Okay. So what describes, so if we have a probability distribution, what are the things that describe the probability distribution? What are the characteristics we should look for? The mean, for example. And so the mean is what? The mean that we usually write like this, k, or like this, depending on the books. Okay. How can I get the mean value for k? I know that P of k is the number of occurrences divided by the total number of events. Okay? So I have 1 over the total number of events, okay, times k times the number of times that k occurs, right? From the minimum k to the maximum k. In this case, it's small n. The number of events is not the n here. Okay? It's the number of, this n is the number of coins. The number of events is the number of times we toss the coins. So in this particular case, as I said, unlike the case, for example, of the distribution of the number of glasses, the number of glasses, people wearing glasses in class, the total number of events is not finite in some sense. We can keep tossing coins as much as we want. So we have to just take, but we know that the ratio nk divided by n is the probability. So we can write this as sum over k that goes from 0 to n, k, p of k. Okay? So what's the average value of k? Well, I have to multiply k by the probability of having k and sum over all the possible k's. Okay? This is always like this. If I have a probability of a number of an object, in this case, this event is described by. Sometimes we cannot take the average of something. Okay, so an event can be, I don't know, either red or black. So you don't take the average of red. It was reddish. Okay, but in this case we can associate a number. Okay, and to the event, and the number is k, the number of occurrences of tails, I don't know, or heads, or okay, and we can write down the average of this number. Okay, so we have to sum over k this thing. So now I'm going to do this calculation here with the binomial distribution. Do you know already the result? No? N times? Okay, it's certainly proportional to n, right? Because the larger n, the larger the average value of k can be, because this thing scales with n. Okay, k goes up to n. And okay, so let me show you that this is n times p. So the number of times, but this has to be like this, right? Because this is the number. These are n. The n coins are independent, and each of them can give a head or a tail. Sorry, with probability p. So the average number of tails in n coins should be n times p. Okay. So we have collected the information about the n coins in the binomial distribution. This made it a little bit more complicated, but we should never forget that the coins are independent. Okay, so let's do the calculations. We have to. We do the calculation because it contains. We have to use an interesting trick. Okay, so this is the sum. First of all, this sum for k equals 0, the term is equal to 0, right? Because you have 0 times something. In this case, we would have 0 times 2 to the minus 11. So we can start from k equal 1 up to n. Okay, and then k divided by k factorial is what? Is k minus 1 factorial, right? Because k divided by k factorial is k divided by k minus 1, blah, blah, blah. So if I erase this, I just have to start multiplying from k minus 1. K minus 1 factorial, and then I have n factorial, and then I have n minus k factorial, p to the k, q to the n minus k. So let's take one of the n, let's put it out. Let's take one of the p, let's put it out. We have n times p, and then we have this sum, k equal 1 up to n of n minus 1 factorial divided by k minus 1 factorial. And then we have, let me write this as n minus 1 minus k minus 1 factorial, and we have p to the k minus 1, q to the n minus 1 minus k minus 1. Okay? I just took one of the n that comes in n factorial and put it out, and one of the p and put it out, so this becomes p to the k minus 1, this becomes n minus 1 factorial. Now, if we call k minus 1 t, okay, then k minus 1 goes from 0 to n minus 1. So t goes from 0 to n minus 1, n minus 1 factorial divided by t factorial, n minus 1 minus t factorial, p to the t, q to the n minus 1 minus t. But the sum is what? Yeah, it's 1. P plus q. It's the same normalization condition we had on oh, by the way, when we, if these are mutually exclusive and blah, 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 they cover all the space of possibilities, when I sum over all the possibilities, P of k has to be 1. This is usually called the normalization condition. Okay? So you normalize your probabilities. So this is p plus q to the n minus 1. But p plus q to any power is 1, because p plus q is 1. So this is equal to np. So I just wanted to show you how to do this calculation, because mostly the calculation with binomial coefficients are always this. You always have to use these sorts of tricks. Okay, pull out some k, pull out an n, write n minus 1 factorial, k factorial, and so on and so forth. So it's a very universal trick. It's not that I like to do this calculation in the blackboard. Okay, so the average of k is equal to n times p. Yes.
Can I say n times p is the area on the pk diagram?
No, the area under this diagram. Okay, so first of all, this is discrete. Okay, so if you take, I don't know, you build it like you build a histogram, then the area under this curve is 1, right? So I have to, in order to get the average of k, I have to take pk and multiply it by k. So this thing gets a little bit gets multiplied by a line. So this part goes up a little bit with respect to this part, and the area under that curve is the average. Okay. The area in this sense, you have to build the histogram, and then. Okay, so there are other things we can calculate. We can calculate the average of k squared. And there are actually, okay, so let me tell you the result. I don't want to calculation. So the average of k squared is n squared p squared plus n p q. There are many ways you can do this calculation. You can just put k squared in here and then work a little bit and then come up with this expression. Okay. There is another possibility. You can write k as sum over I that equals 1 goes from 1 to n of epsilon I, and epsilon I is an indicator variable. If the I coin is tail, then it's 1. Otherwise, it's 0. Okay, this is a way to count. In each of these variables, so the probability of having epsilon I equal to 1 is equal to p. The probability of having epsilon I equal to 0 is equal to q. Okay, so there are other ways in which you can do this. And these are independent events. So the probability of epsilon 1 being equal to 1, epsilon 2 is equal to 0, is the product of the two probabilities. So this is another way you can compute this quantity here. okay, for example, I'm showing you this because it will be relevant in the for the statistical mechanics part, because this can be occupation numbers. So if a level might be empty or full, an energy level might be empty or full, and this will be the statistics will be dictated by the distribution of the F. So for example, I don't know, if you want the average of k square, you take this sum square, okay? And so this is the average of the squares plus this sum here, okay? But here the simplification is because the epsilon I square is equal to epsilon I, because if epsilon is either 1 or 0, if I square it, I still keep 0 and 1. So when I do the when I do the average, I can just neglect the square, and the sum of the average is equal to the average of the sum. Okay. And the same thing here; these are independent, and then I can get the result. Okay. So so just to tell you that there are several ways of doing this calculation. You might want to exercise with all of them, such that when we talk about it in statistical mechanics, you have. But one thing that I wanted to show you is that this thing here is the average of k squared. Okay? So, sorry, I need a little bit of room here. So the average of k squared minus the average of k squared is equal to n times p times q. What is this thing called? The variance, or the standard deviation. So, for a binomial distribution, all the moments exist. Okay, if I calculate k to the 1075, for example, this is something. Okay, this will be, it might be a bit complicated to calculate. Actually, you have an analytic expression for all the moments, but you know, this is a number, it's something. Okay, so this is not true for all the probability distributions. Okay, it's true for the probability distributions which are bounded. Because if a probability distribution, if k can be only up to a certain value, let's say n, then k, the average of k to any power has to be less than the maximum possible k to that power. Okay? So I don't know what this is, but this is certainly less or equal, depending on p and q, to n to the 1075. Which is finite. This is not true for all the distributions, and this is important. Sometimes it's very important in statistical physics. Let me give you an example. I'll give you a couple of examples. The first example that I want to discuss is okay, let me erase this. So do you have any questions? Are you familiar with this sort of calculations, averages, binomial, and so on and so forth? If you're not familiar, you should do a lot of exercise on this. So for example, let's assume we have a random number. Okay? And this random number is an integer, and it's any integer. Okay. So k is any integer, except maybe 0. Okay? Let's say any integer except 0. And p of k is proportional, inversely proportional to k squared. So first of all, now I want to understand how this probability distribution behaves. Okay, so first of all, what should I do? What should I compute first? C, the normalization, right? Otherwise, I get all the moments wrong if I don't have the normalization correct. So how can I find C? Well, I have to impose that of P of k is equal to 1. Okay. But this thing is equal to C divided by k squared. So this is C. Okay? So first of all, is this sum finite or not? It's finite. Do you know which number is this? Pi square over? Pi square over 6. That's correct. This is the Riemann zeta function in 2. Riemann zeta function on the even numbers, it's easy to compute. It's always pi to some power. So do you know zeta 4? Pi to the 4 over 90. Very good. You know your zeta functions very well. This is pi square over 6. Very good. So C is equal to C over pi square. Let's do 6 over pi square. Okay, so actually this should be 6 over pi square. Okay, so this is a well-defined distribution. The only thing we ask about the probability is that they are positive and they sum to 1. What's the average of k? The average of k should be sum times k. And what is this? It's infinite, right? It's not convergent. This sum is not convergent. Yeah, it's the harmonic number of order infinity. So if I put, so this diverges like if, so a mathematician would say, okay, this is infinity, so this moment does not exist. Okay? It's infinite. A physicist tries to say a little bit something more, less rigorous, but something more. For example, I mean, there is no infinitely large number in physics, right? There's always some sort of maximum. So if you put a lambda here, a cutoff, this is called a cutoff. So we cut this sum up to not infinity, but some large cutoff. Then this goes for lambda large, like lambda, like the logarithm. Because for very large lambda, I can approximate the sum with the integral. Okay? So you always have to think about, when the divergence is at infinity, it's always good to approximate the sum with an integral and try to see how the integral diverges. So this goes like the logarithm of lambda, plus other stuff. It's not exactly the logarithm of lambda. In fact, In fact, this thing is called the harmonic number, as you say. So there are constants, there is something which goes to 0 like 1 over lambda and so on and so forth. But the important thing is that this diverges like log lambda. Okay. So what does this mean? I mean, if we have this random number, so first of all, okay, so this goes to infinity. So this moment does not exist. And you can also see that the higher moments do not exist. If I put k square here, I get k square here. I get sum of 1, which diverges not like the log, but like lambda. But still, it's a divergence. Okay, so no moments exist. This is a well-defined probability distribution, but the average does not exist. So we can generate these numbers, okay? And we can look, so for example, we can do like 100 trials, okay? And we have 100 trials. All the numbers that we get are finite numbers. We can get the average, just, you know. We get, I don't know, K1 up to K100. Okay, we just sum them. So this is the first number generated randomly. I don't know, 1,376,000. The second number is generated randomly with this probability distribution, 3. The third number, and so on and so forth. So I have a collection of 100 numbers, okay? And I do this. This is a finite number, right? It's a sum of finite numbers divided by a finite number. It's a finite number. What does this calculation mean? Why do I get infinity here? Because when I keep increasing this, instead of taking 100, I take 1,000, 10,000, 100,000, okay? This number goes all over the place. If I do the same experiment with the number which is distributed with the binomial distribution, this number will rapidly converge to the average to n times p. But here, this number will just fluctuate and oscillate and never converge to anything. Okay? So this is the meaning of non-existence. If the moment exists, then when we do a numerical experiment, when we take a sufficiently large sample, then we actually see, we measure that moment like this. We do we sum all the numbers that we got, and we divide it by the size of the sample, and we get something which is close to the moment which is predicted. Otherwise, we have no way of predicting this. Actually, it's not true that we don't have any ways. We have some ways of predicting this, because these are random numbers, right? So their sum is a random number. I can think about this sum 100, I don't know, as a random number as well, and calculate its probability distribution. This is usually done in physics. But this number here certainly will not converge anywhere. Okay? The idea is that the tail of the probability distribution is not, for large K, this probability distribution goes to 0 too slowly. So there are rare events which occur at large K, in which K is really, really large, where we can actually have, they can occur with a probability which is large, and therefore this sum goes all over the place. This is the reason why these moments do not exist. So you don't have to be afraid by probability distributions which don't have moments. They have actually a very important meaning for some parts of statistical physics. So they exist. Okay. So the same, if we change this, instead of c divided by k squared, we put k to the 4th, then the constant, as our friends told us, is not 6 divided by pi squared, but it's 90 divided by pi to the fourth. So the first moment will exist, the second moment will exist, the third moment will not exist. Okay. So let's now talk about continuous random. Is this clear? You have any questions? All right. As I said, if the distribution of the case is bounded, if this is like this, but then goes to 0 and stays 0, like for the binomial distribution, where the bound is n, we cannot have any k larger than n, then all the moments exist. If the distribution is unbounded support, I mean, then it has to go to 0 sufficiently fast in order for all the moments to exist. Okay? It has to go to 0 certainly faster than 1 over any polynomial. For example, an exponential distribution, e to the minus k, that will work. Okay? Because sum of any power, sum of k to the any power times e to the minus k, this is always finite. Becomes large, but stays finite when the power increases. Okay, so let's now talk about continuous random variable. So let's take the simplest case of just a single real variable. Okay, let's call it x. If we have a real variable, clearly the probability of having a particular value of the real variable, most of the cases, is 0. Because we have to specify all the digits of the real variable, and these are infinite in number. Okay? So we don't talk about the probability of the value of a variable, but we talk about the probability that the value of the variable is in a given interval. For example, we can talk about the probability of x belonging to alpha beta. This is a meaningful thing to talk about. For our class, it will be enough. I mean, you can. So, first of all, let this concept sink in your head. So you don't talk about the probability for a real variable. You talk about the probability for a real variable to be in a given interval. Okay? In this class, we will be content with the following thing. Suppose there is a function, small p, such that this probability is an integral of this function between a and b. Then p of x is called the probability density Okay? If x is a real variable, clearly the worst that alpha and beta can be are minus infinity and plus infinity, right? Then we cover the entire real space, and then this integral has to become 1, because we are covering all of the space, so the probability is 1. Not only that, but we can, yeah. The probability of being an interval and in another interval, if the intervals are disjoint, are mutually exclusive. The probabilities are mutually exclusive. The probability of having both things is clearly 0. Okay, so P of x is positive. The probability density should be positive. If it is, suppose that P of x is negative in like something like this, then what's wrong? Because here I'm only talking about integrals, but this probability has to be positive. So could it be that the probability density does something like this? No. Why not? Say it again. Uh-huh. Yeah, but this is a probability density. If I take alpha and beta, which cover just this part here, then the integral of a negative function, is negative. And this cannot be. Okay? So P, if you can choose this alpha and beta as you want, this P of x has to be positive.
It doesn't have any meaning if it's negative, right?
Hmm?
It doesn't have any meaning if it's negative.
Yes, but because it doesn't have any meaning if it's negative, because you can choose alpha and beta in that interval there, right? If you're not allowed to choose alpha and beta as you want, this function is only defined by the integral. Okay.
Sure, but even I think we cannot have such kind of thing like at the beginning. So it is meaningless to have something and the occurrence of something is negative.
But why? This is what I'm asking. I know it's meaningless, but I'm asking you why. How can you prove that it's meaningless?
I mean, something is okay.
P of x is not measurable. Okay, the only thing we can measure is probability of x being in an interval. So that's, I'm asking you, you can build a paradox like this one based on the fact that you can choose alpha and beta that cover just that interval, and then you cannot have the probability density, the probability there to be negative. Or another thing will be if you have alpha fixed here and you increase beta, if I increase the interval, the probability should only go up, because I'm increasing the possibilities for my random number to be in. If the integrand is negative, the probability in a range goes down, and this does not make any sense.
Yeah. Maybe one can define like probability like in quantum mechanics, and then beta squared, and then you say that. Yeah, I mean, it's just.
Well, I mean, it's just saying that the positive function can be written as the square of any function, but why would you do that in general? I mean, this is a more general.
I think it's up to us, right?
Hmm?
I mean, it is up to us. I mean.
Sort of. I mean, there are some mathematical structures. For example, you require that this function is in the so-called L1 space, the space of integrable functions. If you change structure and you go to quantum mechanics, you say that the function have to be in L2, then the behavior of the vector space changes completely, because L1 has completely different behavior than L2. So for example, one example of continuous probability distribution that you have certainly looked at is the probability density, which has this form. Okay, what is this form called? You know, Gaussian distribution or normal distribution. Normal because it's so common that 2 sigma square. With so the average of these. So this is a function form. So first of all, you should check by doing the integral that the x of p of x is equal to 1. Okay? And then we can calculate the average of x. So this function has support over all the real space. Okay, it looks something like this. Suppose mu is here, it looks something like this. And the width is sigma. Again, let's do this integral. Okay, so let me show you how to do this kind of integrals. What would you do, first of all? Integration by parts. That's one possibility. Gamma function. You want to transform the exponential into what? Expand in power series. And what?
If we differentiate e raised to x, we will have 1x. So e raised to x squared. If we differentiate once, we will get like x times e raised to minus x squared. So I mean, I can write that.
Integral by parts.
Okay.
That's what he said. Yes, that's what he said before. Yes. No, I wanted to understand what you. Ah, okay. Okay. Yeah, but there is actually an easier way. You can change variables?
No.
What did you say?
We first use a result for e raised to minus x squared.
Speak up, I cannot hear you.
We first use the result for without the x. We have the result without the x. So we take the derivative of that.
That's. But with respect to what? You have.
With respect to the coefficient, the constant.
Ah, so you have to put a constant here, then take derivatives. Okay, but. If you take derivatives, then you get x minus mu squared down, not just x. Okay, so there is an easy way. When you have this thing, you just change y is equal to x minus mu. Okay? Then it becomes the integral in dy, y plus mu, e to the minus y squared divided by 2 sigma squared, 2 pi sigma. You split the integral. the integral with y is equal to 0 because it's antisymmetric. And the second integral is mu times the integral of this function, which is 1. So this is mu. Okay? If you have higher powers of x, in the end you have to do something like integration by parts, which then give rise to gamma functions and so on and so forth. But for this one is particularly, whenever you have a function, which always happens a lot for random variables, which is just you have a function that for example, the integral of this function is 1, but it's calculated not in x, but in x minus mu, or x divided by sigma. You just change variables. Okay, so the troubles get shifted in the other part of the variable, but usually this part is much simpler than this. In fact, for example, here it's just linear, so I can use the linearity of the integral, and I get 0 plus mu times an integral, but I know that the integral is 1, so I don't have to do any integral there. Okay? So I can also calculate the average of x squared, and this you should do as an exercise. Okay, calculate the average of x squared, and when you subtract the average of x squared, you find sigma squared. Okay, so for example, let's take another probability distribution. P of x is equal to 1 if x is in 0, 1, and it's equal to 0 if x it's not in 0, 1. Okay? So this probability distribution looks like this. First of all, what's the average of x? No, it cannot be 1. Yes, cannot. It's a half. It cannot be the largest value. The average is never the largest value, unless the function is completely picked on the largest value. So the average of x is 1/2. Let's see if it is true. What we have to do, the integral between 0 and 1 in dx of x. Okay? This is x squared divided by 2 calculated in 1 minus x squared divided by 2 calculated in 0. Okay? This is 1/2. What's the average of x squared? 1/3. Right? Because this is the integrand dx of x squared, which is x cubed divided by 3 calculated between 0 and 1. And from here we can get the variance, x squared minus average of x squared, which is 1/3 minus 1/2 squared, which is 1/4, which is 1/12. Do all the moments of this distribution exist? What do you think? Yes. Why yes? Because the distribution is bounded. And do you think the moments of this distribution grow with, so if I ask the average of x to the n, does it grow with n? No. Why? So, without doing the calculation.
Because it is between 0 and 1, which is less than 1, and then
And then I can put a bound here, right? This is less than the maximum x to the n, right? This is for positive x. So this is 1. And in fact, if you do the calculation, it's very easy. It's just put n here. So the integral is 1 over n plus 1. So this goes like 1. This is equal, actually. 1 divided by n plus 1. So it goes to 0, 1. Okay, let's look at the last example. The last example is actually a very interesting distribution too. It's a Lorentz distribution. This is a distribution which has very long tails. So when x goes to infinity, it's not like, compared with the Gaussian distribution, this looks something like this. The Gaussian distribution looks like this. You have a question? A must be positive, yes. The probability is a function of x. A is a parameter. You can put it to 1 if you want. I just put it because A gives you, so I wanted to discuss this distribution for the following reason. First of all, what's the average of x? Yeah. You got the right answer for the wrong reason. No, it's the correct reason. Actually. So it's 0 because it's symmetric. Okay? But, okay, we have to specify. Because since we are physicists, this is enough. Okay? Because for a mathematician, this integral, let's put 1 instead of A. It's a bit, because this integral, when x goes to infinity or to minus infinity, this goes like 1 over x. So it's not integrable, neither at infinity nor at minus infinity. But if you substitute infinity with the same lambda to the right, to the left, then you can use this argument, the argument of it's symmetric, for any lambda. So if you take the lambda that goes to infinity, limit, you get. But for a mathematician, the correct definition is when you have two different lambdas here. And the limit when one goes to infinity, they both have to go to infinity, but not like the same variable. One can go to infinity faster in some sense than the other. So, and in this case, you will not get the result. And in fact, if you try to estimate the average, by taking random numbers from this distribution, so you take random numbers distributed with this distribution, the mere sum of these things divided by the number of times you do the extraction, this does not converge to 0 very well. Okay? It goes all over the place. So you get positive and negative and positive and so on and so forth. So in this sense, the average is 0 because it's symmetric. But if you go and actually try to match the average from what you get from the experiments, you get things which are all over the place. This thing actually looks something like this. Somehow wants to be 0, but never. It's certainly true that inside the second moment does not exist, because this integral will diverge. Okay. So we are used to say that for the normal distribution, the variance is the width of the distribution, right? So we wrote it before. We wrote this is sigma. For distributions like Lorentz distribution, in which the variance does not exist, we cannot make the same argument. Okay? But still the distribution has a width. Okay? For example, you can define the width by the value of x, after which the probability of finding something drops by, I don't know, 1/2 or 1/4. Or you can define, or for example, you can define the width of the distribution as the two values of x that contain the interval that they have to pick that contains 70% of our of the probability. Okay, so this is, for example, when you see growth charts for children. Have you ever seen this? You don't have, so growth. So if you have a baby, okay, your doctor measures it. Okay, says, oh, it's long, it weighs so much. Okay, so you put here, for example, the age in months, and it's true. I mean, and here you put, I don't know, the height of the baby. Okay, and you have curves like this. So at 0 months, of course, the baby is not 0 centimeters, but usually born something around 40, 45, okay? And then it grows like this. But then, this is the average, okay? But the doctors never look at whether your baby is actually exactly on average. But they have these things here, the percentiles. Okay? So this is the average coincides in this case with the 50th percentile. So it means that 50% of for example, at, I don't know, at 1 year, 12 months, okay, there is a value here, which is, I don't remember, something like 70 centimeters, okay? Then depends whether it's a boy or a girl, and depends on many things. So this line here, let's say this is 70 centimeters, okay? What does it mean, this thing? Means that at 12 months of age, 50% of the babies were below 70 centimeters and 50% were above. Okay? And here they put something like 75th percentile. Actually, sorry, 25th because they counted from here, and here is 75th. And here they put something like 96, and so on and so forth. So, for example, if this is, I don't know, what is this? Something like 65 centimeters. Okay? So it means that 25. Oh, sorry, 4. Okay? So it means that if at 12 months of age, 25% of the babies were 65 centimeters or less, and 75% were taller than that. Okay. So, and you can do this game for, so the doctor is happy if your baby stays within this thing here. And you can define this as being the width of the distribution. They don't tell you what's the distribution, which actually is pretty well approximated by a Gaussian distribution. For any slice here, there is a Gaussian distribution, more or less, except the tails. The tails are different. Okay? And so this is the width of the distribution. You can define it as in this way. And this is the correct way to do it also if there is if the average does not exist. Of course, the average height exists for human beings because, first of all, we are a finite number, large but finite. And second, you can put a clear, easy upper bound like 10 meters. Nobody's ever seen somebody higher than 10 meters. So certainly all the moments of the distribution have to exist. Okay? So just to say that for the Lorentz distribution, A is the width of the distribution, but the second moment does not exist. A is the scale. Okay? I can write this probability distribution of x as 1 over pi, 1 over a, like this, okay? So if I define the new variable y, which is x over a, and I look for the probability distribution of y, the probability distribution of y is 1 over pi, 1 divided by a, 1 plus y squared, but then there is another term here, right? Because when I change variables, the probability distribution change by the Jacobian. Okay? Why is this? The Jacobian for this thing is dx by dy. It's always dx by dy, which is equal to a. So this is 1 over pi, 1 plus y squared. The density, why do I have to introduce a Jacobian? Because if I have y, which is a function of x, the probability that, suppose this function is monotonic, okay? Otherwise, I have to have different branches and so on and so forth. When I invert it, I have a problem. So if I want to calculate the probability that y is between f of alpha and f of beta, and f is monotonic, this is equal to the probability that x is between alpha and beta. Because f does something like this. Okay, so this is the integral in the x of between alpha and beta of p of x. If I want to change variables, the dx becomes dx is equal to dy times dx over dy. I don't need the absolute value here because f is monotonically increasing, but if it is negative, then if it is decreasing, then you do. Okay, so the new probability distribution is, if I change variables, is dy f of alpha f of beta dx by dy p of x of y. So the probability distribution of y is this thing here. So you see, it's important that you remember that the probability densities are defined in terms of integrals, because otherwise you don't understand why you get a Jacobian. When you change variables in the integration, you get a Jacobian. That's why the probability density gets a Jacobian. That's what I'm saying. So don't make this mistake when you change from one variable to another. Okay. Are there any questions? The question is about probability distribution of random numbers. Yes.
If we take a random set of random numbers and takes average, can we take an average, or can we find an average?
Can we find the average of a set of random? What do you mean?
Like average, because we said that we can predict the average, or we can predict averages.
No. So you say we cannot predict the average. That's not true. You can predict the average, and in fact you will see that there is the law of large numbers. Okay, that says that essentially, if you take the sum of many random numbers, okay, and you look at the probability distribution of this object, this will be done by. Actually, you'll do this next week. Okay, one of the last two lectures that my colleague Markus Müller will do instead of me, because I'm away next week. Okay, so you'll see that if you take a finite but large set of random numbers, identically distributed, but with a distribution that you don't know, okay, as far as the moments up to a certain value, up to a certain moment of the distribution exist, then the distribution of this new random variable, the sum, okay, which is a random variable because each of these terms here, it's distributed like the Gaussian distribution with the mean of the distribution of each of the variables.
Are there random numbers which do not satisfy this? Because I can always think of random to make this true.
So first of all, you don't have to think about random numbers. You have to think about distributions. Okay? So distributions are, so a random number generator, like the one which is in your computer, okay? It's a black box that takes as input something, like it's called the random seed, and gives out random numbers. It gives out numbers which are not really random. They are pseudo-random. I mean, if you're careful enough, because there is an algorithm behind it. It's not random like tossing a coin. There is an algorithm behind it that generates that. So but for all practical purposes, they are good random number generators. They give you, you tell them which distribution, you tell the algorithm which distribution, and that samples that distribution. So you have to talk about not random numbers, like 3. Is it a random number? It's a meaningless question, right? 5, is it a random number? It's a meaningless question. The question is, I have a distribution like normal, okay? Or Lorentz, or like that I showed you before, 1 over k squared. This is a distribution. You can build an algorithm that generates pseudo-random numbers with this distribution. And you can ask whether if I generate 100 numbers and I take the average of this 100, it's representative of the average of the distribution. For some distributions, this is true. For some distributions, this is not. This is what I wanted. If the moment exists, then if the first and second moment exist, and if all the moments exist, there is a theorem actually. You see but in the situation in which all the moments exist, like binomial distribution, like the normal distribution, like an exponential distribution, a Poisson distribution you'll see next lecture. Then all the moments exist, and therefore you get a good representative of the average. Okay. Yes, you have a question. No, the boundary can be negative. This thing can, the argument. The integrand is positive. Okay, let's put it this way. If f is monotonic, okay, monotonically increasing, then it's okay. If it is like this, okay, then you should break the probability of finding y between this value and this value. It's given by not a simple integral, but the sum of 2 integrals, one on this branch and one on this other branch. Because you can have, so you have to sum the probability, when you invert the function x of y, you have 2 possible solutions for each limit of the interval. So that's why I said, let's take f continuous, monotonically increasing, so on and so forth. But in principle, you can have more complicated situations, but then you have to study how to invert that function and break the integral over, and break the contribution of this p to 2 separate parts where the function is locally monotonic. Okay? So yes, you can have more complicated situation, but you have to be careful. Okay, let's stop here.